Do you know that feeling when your bike just seems perfectly in sync and you feel super confident? I've found that feeling is pretty hard to pin down and almost impossible to quantify. There's a huge list of variables that add up to how a bike feels: frame geometry, suspension, weight, wear and maintenance, even tire choice. But I think a big key to that feeling is bike setup. In other words, how the rider fits onto the bike. The current way we measure and map that fit leaves too much room for error and doesn't provide enough data. So I decided to develop a tool and find some answers. Of course, the bike fitting industry has been working on this for decades, but not enough people get professional bike fits because they're expensive and time consuming. However, I think that everyone can benefit from some kind of guidance when it comes to bike setup. What we need is a quick and repeatable way to get the fit measurements, and it would be amazing if we could access data about similar bikes and riders that we can use to tune our own setup. So this is what I've come up with. It's effectively a smart measuring tool just for bikes. It uses position sensors and a gyroscope to measure the location of the pointer at the end of this cable. It straps to the saddle while the user pulls the pointer to a desired component to measure. Once all the components are measured, the onboard controller can calculate and compare each data point. By doing this, we create a map of coordinate locations and their relations to each other, which we can use as a standardized set of data about the bike setup. Right now, the user interface is simply a serial terminal, but it's easy to imagine an app to do the same job. Let's take a look inside. In the mechanical assembly, the bulk cable is stored on a sprung spool, then routes around a measured spool, which has a diametrically polarized magnet on top. This arrangement means the revolutions of this measured spool can easily be converted to a linear measurement with very little error. From there, it takes an angled path towards the nozzle, which also includes a sensory magnet. It's not necessary to measure 360 degrees with the nozzle, only about 200 or so. So this arrangement works great and keeps the parts count low. Having a closer look at the nozzle, you can see the unique offset design. In order to make the angular measurement as accurate as possible, the cable needs to influence the angle of this nozzle with even the smallest amount of movement out at the pointer end. We could make the nozzle really long and increase the string's leverage over it, but that would mean it'd probably break off pretty easy. So, in order to make it super compact and robust, but still accurate, you'd want to pinch the cable as much as possible so that it reacts to any movement. This 1S LiPo is here just in the prototype. The production version would be empty here, leaving space for the electronics overhead when assembled. In the electronics assembly, we have a main board that runs the tool. It has a microcontroller, a signal multiplexer, a gyro module, and a Bluetooth module. Also in the top half, you can see the two sensors. These are AS5600 contactless position sensors. They measure the position of the spool and the nozzle with a resolution of less than a tenth of a degree. This setup works great for the prototype, but quite a few improvements could be made for the production board. First off, the multiplexer is here as the sensors communicate via fixed I2C addresses, and it could be removed by using a microcontroller like the ESP32, which has multiple I2C buses. In fact, using ESP32 would eliminate the need for a separate Bluetooth module, as well as make FCC and CE certifications much easier and cheaper. The production board would also include an onboard battery and charge controller. A custom sensor board could also be made, maybe with the newer AS5600L, which includes changeable I2C addresses, but these existing modules are very inexpensive and widely available. final assembly is pretty quick as the sensors are contactless and the two halves key together to ensure alignment. There are a few mechanical changes needed to make these parts moldable, but the prototype demonstrates the concept pretty well. Let's have a look at the software side. When it boots up, it first pulls two calibrations from the EEPROM. One is a gyro calibration, done to eliminate any error in the physical mounting of the gyro. The other is a nozzle calibration. This tells the controller when the nozzle is pointing directly down when the tool is flat. Next, it takes a bunch of samples of the saddle tilt angle from the onboard gyro and averages those to set the saddle angle. It uses that angle to correct all following measurements. It also checks that the sensors are reading the magnets properly, then shows a list of possible commands. Next, you use the commands to measure each point on the bike, each of which reads the distance of the cable and angle of the nozzle to create that vector measurement. The final command shows all of the mapped and calculated measurements. But why is this data interesting? In fact, you can get most of these measurements using traditional tools and a bunch of trig. It's interesting because you can map a bike in less than a minute, and it can easily be stored and shared using the app. Users would have a history of measurements they've made for each bike, and the ability to share that info. A database would allow users to search for similar bikes and riders and give details about them, like riding style and general location. It would benefit the cycling community to demystify bike setup by making it open source. Even though no two humans, even of the same height, are exactly the same, being able to compare setups with similar bikes and riders would allow for informed decision making about bike setup. You may have caught it earlier, but there is a bunch of neat data you can capture with this tool that's very difficult to measure otherwise, like weight distribution and the distance the grip is behind the front axle. I think these two things alone play a huge part in bike feel. While I've shown a mountain bike here, this would work for any kind of bike. In fact, with road and aero bikes, you could include unique measurements for each grip position at the handlebar. I think with the right community behind it, something like this could be pretty useful. Personally, I'd love to have this kind of info, and I suspect it would help a lot of folks, regardless of experience level. Thanks for watching.